We're going to look at this one. This is an example of one where we have negative work that is being done. We have a bullet, 0.025 kilogram bullet is fired with a velocity of 343 meters per second. That's actually a very important speed. It's also known as the speed of sound. You don't have to know that yet. Eventually you'll have to know that, at least in room temperature. At a block of wood with a thickness of 0.05 meters. So from one side to the other side, we have a block that is 0.05 meters that is secured down to the floor. When the bullet strikes the block of wood, it exerts 50,000 newtons. Question: if the bullet exerts 50,000 newtons on the block, then how much does the block exert on the bullet? 50,000 newtons, but in which direction? In the other direction. That's where we're going to get the negative work from, because work is equal to force times distance. So what is going to slow this down? It's the fact that we are going to have a negative force times distance, because we are going to have a negative change in kinetic energy. The bullet is acting on the block, 50,000 newtons. The block is acting on the bullet, equal in opposite direction, 50,000 newtons. So our equation is still this. This is says how far does the bullet penetrate the block of wood. We're trying to figure out what is this distance here if we know it goes from 343 meters per second to rest. So this is where an example of the work kinetic energy theorem is very helpful. 1/2 mvf squared minus 1/2 mvi squared. The distance it goes is we're trying to figure out what the distance is, trying to figure out what that is. We just realized that the force is a negative 50,000 newtons because it's slowing it down. It's negative work because the bullet is moving to the right, and which way is the force? Left, and what is that angle? Yes, and cosine of 180 is negative. This is what we talk about with the bookwork, that if the force is in the opposite direction, the negative work is done. We're given the mass of the bullet, and when it's not explicit here, but in both of these, I'm actually going to add some more information. I just didn't include it before. In both of these, the final velocity of the bullet is going to be 0. So it's going to go into the wood, and then it's going to slow down, and it's going to come to rest inside of the wood. And so this is 0, and that's the initial velocity. So once again, in setting this up, it's really just the direction and everything we are given. There's only one thing that we're not given, and we have to solve for that. So the reason why this force has to be negative is if this is 0, we have this negative value there and negative value there. Because our distance has to be positive. It's moving to the right. It goes in here a certain amount. So that's where our equation comes from. I will put it down here. Yes. We have a negative force. I guess I don't have to necessarily rewrite it out again, but I will. Plug and chug. Trying to figure out the... write it out, or it could show that the final velocity is 0 here. So we're squaring that. It's a pretty tough piece of wood. 50,000 newtons. For a bolt to be fired at Mach 1 into a piece of wood and only go 3 centimeters in. Like I said, this goes to 0. When you are calculating, just FYI, when this 0.025 times a half, don't round in here because we could come out with pretty different answers. Oh, sorry, I'm looking at the wrong. So the negative that we have here is going to cancel out the negative we have there, and then thus giving us a distance that is a positive distance. Does anybody have the answer for that one? Yeah, 0.03 or 0.029, either way. Let's write it out so we can see the full magnitude of that. So anyway, it goes about 2.9 centimeters or 3 centimeters, which it's a prototype piece of wood, we'll just say. Reinforced wood. So it did not go all the way through. It only went about 0.029 or 0.03 meters. Now we're basically going to figure out, okay, how fast does it actually have to go in order for it to go all the way through? And we're still using the same equation here, but instead of that, some things that we know, the force is still going to be 50,000 newtons. So in here. So for the second part, that's part 2. F is still 50,000 newtons. We're using a distance. Now here's once again, I created this and I had to actually add some things in. We're trying to figure out exactly how fast for it to go through and just break the other side here. It's not continuing. If it went completely through the wood, you would have to know what in order to solve for this. Yeah, you'd have to know not only how far it went through the block, but you'd have to know how fast it was going after the block. And we'll get to problems like that when we get to momentum and all that. So we have this, and we're basically just solving for what does VI have to be in order for this to take place, in order for it to go through, just to go through the 0.05 meters and stop on the other end. Like I said, it's the same equation. We're plugging in just what we know. We still have a basically 1/2 times, I don't necessarily show it here. It's a little small there. There, refocus it. Oh, that's 0.025. So that all goes to 0. This is where in this kind of these repeatable type of problems where it can be very easy to miss writing the equation down, missing writing 1/2, missing writing the squares for this. Sorry, that's a negative on that side. And calculation, and we got a calculation for the initial velocity needed. Just barely make it through.
447.
Is that what you're say as well? Concur? You? No, that's okay. 447.21 meters per second. Any faster than that, it goes completely through. Now, in the problem, I stated that the block is secured down to the floor. When we do our next chapter, which is collisions, the fact that the bullet went in and became penetrated and stuck inside the wood, we would actually call this an inelastic collision. And if we knew the mass of the block and we knew the mass of the bullet and we knew all this, we could figure out how fast would the block and bullet combination start moving back if we shot into it. because we would know the velocities of that. 447.21 meters per second. Yep. Now, as I mentioned here, the next one, the number 4, this is an energy transformation one as well. We have some amount of energy. It's not dropping a rock, actually throwing it. But as I may have mentioned here, if we go through what are the energies we have at the very top, okay, we have a rock that's being thrown from a certain height, and we're trying to figure out, sort of the energies when it strikes the ground. I had already told you before, I calculated previously, that if we had used kinematic equations, if we had used the 4th equation, you would have realized that it would be going 38 meters per second down. So where in the world must have lost that energy somehow? Now, you did not need to have calculated this, but we can go through and say, hey, is it moving at the beginning? Yes, so there's kinetic energy at the beginning. The rock is being thrown. It is being thrown from a specific height. There's no mention of a spring. And there's no mention of work being done. Basically, we're not talking about, there's no work being done at the top. There's no air resistance. At the bottom, right as it strikes the ground, it does have kinetic energy. We have to realize that it's a different kinetic energy than what we had in the beginning. If there was no friction at all, then these two energies on the left would equal the one on the right. But I'm telling you that there's air resistance here, which is slowing it down, so not all of the energy here is converted into kinetic. Some of it is being converted into work due to friction. So we're not calculating the force or the distance. We're just basically saying, what is that? Because whatever that is, that's how much energy was basically pulled away from due to air resistance. So you should be able to set up this one pretty surely on your own, wherever you choose to solve for it. When we do ultimately solve for it here, eventually comes out to that right there.